All right. Any questions?
You feeling better?
Then,
Friday?
possibly.
Possible.
Physically, yes. Emotionally, no. All right. We last left off. Capacitors. So we know that somewhere around here. That capacitance is the charge over the voltage between the two plates. And this is true regardless of the setup. If it happens to be a parallel plate capacitor, it's also equal to epsilon A over D. Should always beware when I'm about to go off of memory. All right, I'll check. Which is kappa epsilon sub naught A over D. Now kappa is equal to 1 if you're talking about a vacuum, otherwise known as free space, or if air is close enough to 1. We have surface charge density, which is the charge divided by area. We have the electric field, magnitude of the electric field from the plates is equal to sigma over epsilon naught, and the electric field total would be sigma over epsilon, would be sigma over kappa epsilon sub naught. And we have the voltage is equal to negative electric field times the displacement, or if we ignore the symbols and just go for magnitudes, voltage is equal to Ed. And there's another equation, I think that was, or sums it up. So if I have a, let's go for a 20 volt battery, or a 20 volt power supply, it doesn't necessarily have to be a battery itself. 20 volt power supply, and more specifically, it is a DC power supply. At this point, everything we've done is DC, like a battery is, as in the electrons only travel in one way. Eventually, we'll get to the point where we're talking about electrons traveling back and forth, in other words, alternating its path, otherwise known as alternating current. I have two plates here, and let's have the distance between them be 0.1 meters, and let's make these 15 meters by 15 meter plates. The important thing here is that the distance between the plates is significantly smaller than the size of the plates, than either dimension of the plate. So we've got our basic quantities here of capacitance, charge, voltage next, voltage, the electric field strength from the plates, and the electric field strength total. And let's just come up with some base values. This is very similar to, or almost identical, different numbers, but almost identical to what we did on Friday. All right. So, what do we know?
Changing voltage.
Let's work on the language at this point.
Voltage.
The total voltage?
Or
Just
voltage. Yeah, this is change in electric potential or voltage,
Oh, okay.
otherwise known as electric potential difference. That also works. All right, so, sorry, Janice, sorry to interrupt. Did I just not hear it?
Volt.
There we go. All right. Is that all we know?
Oh, we can know. Like, Q. I lost my place.
Janice, what I think they're saying is that if you don't know it, nobody knows it.
Wait, is that Q or is that thing?
Yeah.
Whatever.
That Q right there,
Or is
or
that
the sigma?
sigma? Yeah. Is that supposed to be Q or sigma?
Say it again?
Is that supposed to be Q or sigma?
That's supposed to be Q.
Oh.
You want me to throw a sigma in there? Does that help you? All right, we're on a roll here, just cruising right along. Let's recap what we've done. 20 volts is the voltage across the capacitor.
Can we solve for Q? Can we solve for Q by doing, the capacity times voltage?
We said we don't know the capacitance yet.
So
Oh.
the 8.85 value, is that a constant for something?
The 8 point,
The 8.85 value?
that's 8.85 times 10 to the negative 12, that's epsilon sub naught.
Okay.
Is there just air in between the plates?
Yeah, or nothing.
Okay, so you would just do epsilon sub naught times the area divided by the distance between the plates, right?
Yeah, so we can use this formula right here to find the capacitance, because kappa is 1, because there's nothing in between, or nothing of note. Area, we have the dimensions, and the distance between them is given. So capacitance becomes the 8.85 times 10 to the negative 12, times area, which is 225, divided by 0.1. And the answer is 7. So it's 1, 2, 3, 4, so it'd be something times 10 to the negative 8.
1.99.
1.99 times 10 to the negative 8
Yep.
units.
Nanofarad. Yeah, nanofarad. Or farads.
To farads. If you want nanofarads, as the population seems to desperately want to be 19.9 nanofarads. All right. Now, when we do the lab, we're going to be working in the realm of nanofarads for part of it. We'll have much smaller plates, obviously, because 15 by 15 meter plates would be, I'm not sure would fit in the room. But the distance between them is going to be significantly smaller, such as it'll be a couple sheets of paper thickness, distance between them. All right. Now we can go with, I think Janice suggested it. Apologies if someone else had done it. Finding Q.
C times change in V.
Yep. And so that becomes 398 nano somethings. All right. we've gotten this far.
So,
Find sigma,
All right, so what's sigma?
I'll just keep it by A.
And so we have 398 nanocoulombs over 225 square meters. So this would be 1 let's see, what is 1.9?
7.
Seven?
Sorry, 7.
Nanocoulombs per square meter. And by the way, coulomb is a capital C. I was noticing in the lab, some of you wanted coulomb to be a lowercase c. It is a capital C. And the difference between the two is that I know is a lowercase c because it's the same size as the lowercase n. The c has to be bigger than the n. This is, I guess, a natocento, it's a prefix. I guess would be 10 to the negative 11th. All right, now what?
so then we just divide it by, or divide sigma by, keep reading the word, by 8.85 times 10 to the negative 12
Okay,
to find the electric field of the plates in total.
the plates and total you said, or
Yeah.
total?
Both,
Both.
yeah.
Why is it gonna be the same answer?
Because for total, it wouldn't be the same answer unless you have something in between the plates.
Right, yeah, okay. So I have 1.77 times 10 to the negative 12 divided by 8.85 times 10, times 10 to the negative 9th, times 8.85 times 10 to the negative 12.
200 nanocoulombs, or Newton per coulomb, I keep saying that. Newton per coulomb.
How else could we have found it? Oh, and this is the same as Zhao was laying out. I didn't explicitly write it up there, but it is written up there in source. How else could we have found the 200 newtons per coulomb?
For the plates,
Yes.
the Q over A times epsilon.
Oh,
Is that what you're talking about?
no, I mean, basically you just took that and substituted into here.
Oh, I thought that's what you were asking.
Voltage divided by the distance.
Yes. From this right here, this E right here, this is the total.
Oh, yeah.
So 20 volts divided by 0.1 meters gets you 20 volts per meter, or 200 volts per meter, or 200 newtons per coulomb. Questions to hear? All right, so now what I want to do next double capacitance. What are different ways I can double the capacitance?
Decrease the distance between the plates.
Okay, do what?
Hmm?
What do I make the distance?
Half of what it was.
All right, so the distance from 0.1 meters to 0.05 meters, or 5 centimeters. All right, so I could bring them closer together. From over here, the size of the plates doesn't change. Epsilon sub naught doesn't change. Kappa is still 1. It's officially going to stick a 1 in front here. So all we're doing is just cutting the denominator in half. All right, what else could we do?
Double the area.
So area from 225 square meters to that is 450 square meters.
You can stick something between the plates. K equals 2.
Not a K.
Not K? I'm bad with words.
Someone would help me out with what Greek letter that is? Thank you.
Kappa.
Kappa from 1 to 2. Let's see, that's all the stuff that's straight from that formula right there. And there's potentially something else that can happen. What would happen if we made it a 10-volt battery? Would that double the capacitance if we made it a 10-volt battery? I got a slight nod on one, and a couple people, I got two slight nods, yes, and a couple people who are still just wondering. That seems to be in one diagonal. I'm not quite sure, a yes, no, I guess that's a maybe. All right, for a parallel plate capacitor, this equation here, this must be true. If I cut the battery in half, does any of this change?
No.
All right, so the capacitance is not going to change. What does change? If I cut the voltage in half, what changes? What else changes?
Q.
Yeah. So if I cut the voltage down, so let's say I have some sort of variable potentiometer, I cut it in half, basically I'm reducing the amount of charge on the plates. So in essence, what happens is that as I cut the voltage down, there's less push against the electrons, and so the electrons in the plates will go, wait a second, some of us can return home, and they'll basically get pushed back, or off the plates at least. Because remember, I have a bunch of electrons here which all hate each other, and they're trying to get away from each other. So once I reduce the pressure for them to get onto the plate, some of them will leave. All right, so then let's see, if I want to double the voltage, what are things I could do to double the voltage?
Bigger battery.
Okay, so take the voltage of the battery from 20 volts to 40 volts. When I say double the voltage here, I should change that to double voltage across capacitor.
Increase the area, or double the area. Wait, no, sorry, not area, double the distance between the plates.
You have to do something else first.
Half it. Wait, no.
You have to do something. If you half the area and then double the area, then I don't think it's going to change the voltage.
Would changing the plate size change the voltage at all?
No, not unless you do something else first. This comes to, for this type problem, this comes to a very important part of how do we know, I mean, Janice is the one who told us 20 volts to begin with. Why did you say 20 volts?
Oh, because, it's like, as it moves, it's losing its, not charge, but like, as the voltage is moving because of the transition from the positive charge to the negative charge, it loses the voltage, but then gains it again.
Okay, in essence, Kirchhoff's voltage rule or loop rule, if I start at any point, the whatever gains and losses I have, my total voltage is 0 when I get back to where I started. So I gain 20 volts here, I have to lose 20 volts there. So, if I'm not changing the battery, because that one's already been said, if I'm not changing the voltage of the battery, how do I change the voltage of this? When you did your analysis and said that 20 volts across here, did you take into account the size, the shape, the distance, anything? So therefore, oh, this is a chance for someone to just show great insight for me to go, yes.
Would you just change one of those elements?
Say it again?
Would you by changing the size or the shape, would that affect how the voltage is carried throughout the battery?
Throughout the, no, it would not affect the battery.
Oh, okay.
Katie?
Those have nothing to do with it.
Okay. So as long as this 20-volt battery is attached to it, it's 20 volts across here. That's not going to change. I could add other circuits to it, but that's, or other components to it, but that's a different problem. So this, as long as it's attached to the battery, the voltage across here is set. This becomes critical in a moment. So it's fixed if attached to battery. Therefore, if I want a different way of changing the voltage across the capacitor, what do I need to do first?
Disconnect it from the battery.
Yes. Disconnect, and then, now, let's talk a little reality here. If I actually had a capacitor that was charged up, I had it hooked to a battery, got the capacitor charged, and then I tried to disconnect it. In reality, I would need to disconnect it so incredibly fast, because if I do it, if I just normally just use my finger and I throw the switch like that, just as it breaks, there's going to be a small little gap right there, and it'll spark. And it will lose, basically the capacitor will discharge as I disconnect the battery. So, because this is a board problem, we can do this, and with the right equipment, you can do it in a lab too. We just don't have that equipment. At least I believe. There was someone on the internet claimed that it could be done. So it must be true. But on the board problem, we're going to assume that we have that ideal disconnection, that we will be able to disconnect so quickly that we are not going to discharge. Therefore, given our nice ideal disconnect from the battery, what will now be fixed? Yes. So when disconnecting, or when disconnected, charge is fixed. Because there is nowhere for the charge to go. So now we disconnect the battery. Now how do we double the voltage across the capacitor?
Double the distance between the plates.
Do what?
Double the distance between the plates.
Because if the charge is fixed, that means the electric field is fixed. And if the electric field is fixed, then the voltage is directly proportional to the distance between them. Disconnect, and then double distance.
That's doubling the distance between.
The plates, we're just going to push them farther apart. And I'm going to write over margin off screen for the video. This, and apparently, really bad marker. So I'm gonna write the initial values we had. So this was 19.9 nanofarads. Charge was, and the sub-zero is just indicating this is the original value, 398 nanofarads. The voltage was 20 volts. The electric field from the plates was 200 newtons per coulomb. The electric field total was 200 newtons per coulomb, and sigma was 1.77 nanocoulombs per square meter. Questions before I start erasing? All right, so what we're gonna do is we have it initially hooked up like that, and then we are going to disconnect battery. Double separation. And then add dielectric with a dielectric constant of, let me get 3. And then we'll reconnect battery. So originally, this is C0, Q0, delta V0. Oops, got my 0 over here. I'm going to call this E0, E0, and sigma 0. All right. So what we're going to do is, as we do each of these things, what happens to the values as we do these things? So when I first disconnect the battery, what is going to change?
Bless you. The voltage would not be fixed. So then-
Pardon?
Wait, what was your question?
All I've done, so the first step, disconnect the battery. All I do is disconnect the battery. Which of these values will change?
Voltage.
Okay, so what is the voltage now? Voltage, this voltage across the capacitor. It is not 0. Or what is the same?
Pass.
You're saying capacitance is the same?
No, because
Did any of these things change?
distance.
All I did was disconnect the battery.
Oh, okay.
We're doing this step by step.
Oh, okay.
So when I disconnect the battery, did the capacitance change?
No.
All right, so capacitance is still whatever the original was. Does the charge change? Not with our nice ideal
Yeah.
disconnect. So capacitance doesn't change, charge doesn't change. What about voltage across the capacitor?
20 volts.
It's still 20 volts. It's this equation right here. If C and Q stay the same, delta V's got to stay the same. If the charge stays the same, what else definitely has to stay the same? I guess if charge and area stay the same, sigma has to stay the same.
The electric field of the plates.
That's going to stay the same? You seem unsure. Is Jabez right? Yeah, they back in, huh? You are. Right here. Sigma doesn't change. Epsilon sub naught's a constant. So, and there's still nothing between the plates. So disconnecting the battery actually doesn't change anything other than the fact that any other changes will now have a different effect. All right, so now we double separation. What is going to stay the same? Yes. All right, anything else right off the bat you know is going to stay the same?
The electric fields,
Why?
since it's just sigma divided by epsilon sub 9.
So
So then
sigma stays the same.
sigma stays the same.
Okay, so sigma stays the same, and so this electric field here will stay the same, and why is the total electric field going to stay the same?
Because we still haven't added anything here.
Yeah.
All right, so now, not a lot seems to be changing here.
Capacitance would double.
Yeah, we're double the
Wait, no, wait,
distance before. Oh, that was the change to the voltage. Okay,
Wait,
so
no.
capacitance times the capacitance.
Would be half.
Yeah, so this is half of what we started with. And the voltage? Sorry.
That would double.
Okay, someone just said something right before I closed the door? It doubled, yeah, because down here, if my distance doubles, my electric field stays the same, electric field strength stays the same, the voltage, magnitude of the voltage stays the same. So this is 2 delta V sub 9. Then we add dielectric. Dielectric with kappa equal to 2.
Sigma would stay the same.
Why is sigma going to stay the same?
Because it's just charge divided by area, and then charge. Yeah, just charge divided by area,
Okay, and,
and then so then charge would stay the same as well.
all right.
And because of that, then the electric field of the plates would stay the same.
Okay.